Welcome to the video lecturing for BSc II SEM Mathematics for the chapter Functions of 2 and 3 Variables. So in today's class, let us study about the symmetric functions and their partial derivatives. First, let us see the definition of a symmetric function. A function of 2 or 3 variables is said to be symmetric if it remains unchanged when the variables are cyclically changed. That is, f of xy is equals to f of yx. Similarly, if it is a function of 3 variables, then f of xyz is equals to f of yzx is equals to f of zxy. Here, x, y, z are in cyclic order. X is replaced by y and y is replaced by z and z is replaced by x. Then if the function remains same, then such functions are called as symmetric function. For example, here suppose f of xy is x plus y. Let us take one example here. This f of xy is x plus y. Then f of yx means what here? F of yx means you just replace x by y, that is y plus x. So here, is there any difference between these two equations? LHS is x plus y and RHS is y plus x. So it means they are same. So such functions are known as symmetric function. That is, after interchanging x and y in cyclic order, if the function remains same, then such functions are known as symmetric function. Let us take one more example here. This is sine of x plus y plus z. It is function of 3 variables. Suppose it is f of xy, z. So then if you replace x by y, then it becomes x by y, y by z and z by x. Then it becomes what? Sine of y plus z plus x. So it means y plus z plus x is the same as x plus y plus z. So function remains same after interchanging the variables in a cyclic order. So such function are called symmetric function. Similarly, we have this example also. Here also, if we interchange this x, y, z in a cyclic order, the function remain same. So this is about the definition of a symmetric function. Next, let us study about the partial derivatives of such a symmetric function. Suppose we have here u is equals to f of xy is symmetric, then it is enough to find the derivative of u partially with respect to x and its higher order derivative, that is second order derivative of u, that is dou to u by dou x square. If this function is symmetric, then no need to find this uy, that is dou u by dou y and dou to u by dou y square. That is, since of this symmetry of this function, so we just replace x and y in ux. You will get uy. Similarly, in uxx also, if you replace x by y, you will get dou to u by dou y square. Let us take one example here. If z is equals to log of x square plus y square divided by x plus y, then show that x into dou z by dou x plus y into dou z by dou y is equals to 1. First, let us write z as it is equals to log of this x square plus y square divided by x plus y. To make this one as simple, let us apply the property of logarithm. So we know log m by n is equals to log m minus log n. Then first you have to check whether this function is symmetric or not. That is, here this log of x square plus y square, it is a function of 2 variables. If you replace x by y and y by x, what happens? It is log of y square plus x square. It is same as log of x square plus y square. Similarly, this x plus y is also symmetric. That is, if you replace x by y and y by x, you will get log of y plus x. So therefore, this given function is symmetric. So first, let us differentiate this z with respect to x. That is dou by dou x of z. Z is log of x square plus y square minus log of x plus y. Let us differentiate this partially with respect to x. So it is log of x is 1 by x square plus y square into derivative of x square plus y square is with respect to x means it is simply 2x and y is constant, so its derivative is 0. Minus derivative of log of x plus y is 1 divided by x plus y, and the next derivative of x plus y is partially with respect to x, so derivative of x is 1 and derivative of y becomes 0, so it is because it is constant. So this implies dou z by dou x is equals to, simplify this one, it becomes 2x divided by x square plus y square minus x1 divided by x plus y. Since this we have seen here z is a symmetric function, it doesn't make any difference if you replace x by y and y by x. So therefore no need to find dou z by dou y. Here we just replace in dou z by dou x, we just replace x by y and y by x, we will get dou z by dou y. So that is here it becomes dou z by dou y is equals to 2y divided by y square plus x square minus 1 divided by y plus x. So now we want to find here, the given question is you have to find x dou z by dou x plus y dou z by dou y, it is equals to 1, you have to prove this one. So let us consider here LHS, that is x dou z by dou x plus y dou z by dou y is equals to, now substitute the values from equations these two, dou z by dou x and dou z by dou y. This is 2x square, this x into dou z by dou x, here dou z by dou x is this one, multiply it with x, so 2x square divided by x square plus y square minus x divided by x plus y, then plus this y into dou z by dou y, multiply this with y, we have 2y square divided by y square plus x square minus y divided by y plus x. So these two denominators are same. Let us take here LCM, x square plus y square, then add their numerators, it is 2x square plus 2y square. Again these two denominators are same, so we can take these two terms together. Here x plus y is LCM, minus I have taken common, so it is equals to x plus 1. So here take common, here 2 is common, then it becomes x square plus y square and get cancel, minus x square plus y divided by x plus y, and this is equals to, we write this one as here, this is simply 2 minus 1. Let us take one more example. If u is equals to 1 divided by under root of x square plus y square plus z square, then you have to show that x into dou u by dou x plus y into dou u by dou y plus z into dou u by dou z is equals to minus u. Similarly, this dou to u by dou x square plus dou to u by dou y square plus dou to u by dou z square is equals to 0. Here let us take u. Here u is again 1 by under root of x square plus y square plus z square. See here, this is again a symmetric function. It doesn't make any difference if you replace x, y, z in a cyclic order. So it is equals to, this implies u is equals to, take this in the numerator, it becomes x square plus y square raised to minus 1 by 2. Take this one as equation number 1. Let us find dou u by dou x. So this is 1 by 2 minus 1 by 2 into derivative of this one, x square plus y square plus z square raised to minus 1 by 2 minus 1 into derivative of this x square plus y square plus z square is 2x. Partially with respect to x we are differentiating. So it is equals to minus 1 by 2. This is x square plus y square plus z square whole raised to minus 3 by 2 into 2x. 2 to get cancelled. So this these two terms remains. As we want here in second question, we want dou to u by dou x square also. Let us find dou to u by dou x square also. It is equals to, differentiating this once again partially with respect to x. Because it is product of two functions, we have to apply the derivative of product of two functions. So keep minus sign as it is, first function as it is, derivative of x is 1 plus second function x as it is, derivative of this second function is first with respect to power, that is minus 3 by 2 into x square plus y square plus z square whole raised to minus 3 by 2 minus 1 into derivative of x square is 2x. So again here 2 to get cancelled. Now simplify this. So this is the simplified form of dou to u by dou x square. Take this one as equation number 3. Since u is symmetric, no need to find dou u by dou y and dou to u by dou y square, because we have done these two here. So dou u by dou y is equals to here in equation 2 we know the value of dou u by dou x. You just replace x, y, z in a cyclic order, you will get dou u by dou y. So that is dou u by dou y is equals to this y becomes this x becomes y. So y into, and this x square plus y square plus z square, you will get here y square plus z square plus x square. It is same as x square plus y square plus z square only, whole raised to minus 3 by 2. Similarly, dou u by dou z is, here you just replace y by z, you will get minus z into x square plus y square plus z square raised to minus 3 by 2. So now similarly, we want dou to u by dou y square also. Since we have done dou to u by dou x square, in this you just replace, that is you just replace x, y, z in a cyclic order, you will get dou to u by dou y square. So that is here dou to u by dou y square is minus x square plus y square plus z square whole raised to minus 3 by 2. This is same. Then plus 3x is now 3y, and this bracket is again same. Similarly, this dou to u by dou z square is also same. You just replace y by z here, you will get dou to u by dou z square. Let us consider first one. So here we want to find this x into dou u by dou x plus y into dou u by dou y plus z into dou u by dou z. First we consider this one, and similarly how to take the values from equations 2, 3 and 4. Just multiply each term with, that is dou u by dou x with x. Here we have dou u by dou x, multiply it with x, you will get this one minus x square into dou x square plus y square plus z square raised to minus 3 by 2. Similarly, you will get second term and third term. So that is, in all these three terms, x square plus y square plus z square raised to minus 3 by 2 is common. You just take it as common. And the remaining terms are x square plus y square plus z square. Since both these bases are equal, we can add their powers. So it is, after simplification, you will get minus x square plus y square plus z square whole raised to minus 1 by 2. It is nothing but u. So it is equals to this minus as it is. This is equals to minus u. So this is the proof of first question. Similarly, you can put the second one. That is, consider this dou to u by dou x square plus dou to u by dou y square plus dou to u by dou z square. That is, you just add all three equations. You will get 3x square into x square plus y square plus z square whole raised to minus 5 by 2 minus x square plus y square plus z square whole raised to minus 3 by 2. Similarly, next terms also. So again, in all these terms, this 3x square plus y square plus z square whole raised to minus 3 by 2 is common in all these three terms. So remaining terms we can write here x square plus y square plus z square minus, again in these three terms, this x square plus y square plus z square whole to the power of minus 3 by 2 is common. That is, these three terms are same. So we can write it as minus 3 times of this one. So it is equals to 3 into, again bases are equal, we can add their powers, minus 5 by 2 plus 1 minus 3 times of x square plus y square plus z square to the power of minus 3 by 2. So that is, this 5 by 2 minus 5 by 2 plus 1 is again minus 5 by 2 plus 1 is again, this is again what? This is again minus 3 by 2. So these two terms are same, get cancelled, it is equals to 0. So this is the proof of the second example.